on now. There's plenty of classes that you had to cram for between then and now. So, cram and dump. Cram and dump. So let's take the hanging out one. Which one's the greater mass? Let's say M2. So here's a question. What are the forces that are external? What's the system? Let's say the system is M1 and M2. What force is external to the system? Force of gravity, right? So now let's actually think about this. What force would you call the driving force? In other words, that actually drives the system. It would be what on 2? That's right, the force of gravity. So if I'm looking at the net force on the system, I look at all the forces that are external to the system, namely the interaction of the Earth with these two bodies. And so what do we have? We have that the force of gravity on 2 is driving the system, and the force of gravity on 1 is doing what? Retarding the system. It is actually slowing it down, for lack of a better term. What is that going to equal? That's the net force on the system. Therefore, it's equal to the mass of the system times the... That's right. What's the mass of the system, though? That's right. And so here you have Fg2 minus Fg1. What is this equal to? M2 minus M1 times G. And so therefore, what is A? Notice how easy that is. It's so easy. It's disgusting. This is why you can't use it on your lab report. Notice what it does not help you get. What can you not solve using a systems approach? Yes? Why can't you find the tension in the string? Think about it. Phone a friend. That's right. It's internal to the system. All right. So notice, this is killer. This is like, oh my God. But you have to be careful. You have to be careful when using it. Because what is this saying down is? Why? Why is it saying down is positive? Look at it closely. I'm going to zoom out so you see everything. But you have to tell me why it says down is positive. Yes. Okay. And, yes, look at the formula. M2 is greater than M1, so this is positive. Correct. And what do you notice? M2 is going to go which way? Down. So you have to be careful. You can't just follow the systems approach blindly. You have to be careful about coordinate systems. And just to give you an idea, let's do table Atwood with friction. This is great. Table Atwood with friction. M1, M2. What's the driving force on the system? That's right. So net force on the system is Fg1. What's the retarding force on the system? Well, let's just say at FF2. We don't know if it's kinetic or static. And you know what? Let's just whatever. Let's make it kinetic. Who cares? Any other forces on this? Yes or no? Because you have to be really careful, guys. You're going to have to be really careful here. This is not obvious. All right. Because even still, can we truly use the systems approach? I would say yeah. So then what's our system? What's our system here? It's just the two blocks. So this is equal to the mass of the system, which is times the acceleration of the system. So now what's FFK2? By now we're experts, yes. Correct. In this case, it's mu k times m2g. And so what do we end up with? We end up with m1g minus mu k m2g equals m1 plus m2 times a. Notice, what is it? This gave us everything. Like, well, almost everything. It doesn't give us tension. But notice how quickly it gives us our accelerations. Any questions here? Yes? This is how you solve problems on the multiple choice. Right? Because I'm going to be giving you Atwoods, and you have to solve that Atwood in a minute and a half. You think you're going to go through, either you're going to memorize the formula, which is not a good idea. Don't do that. Because I saw what happened last year. Students memorized the formula, and guess what they did? They memorized it wrong. So, bad move. So, don't memorize the formula. Follow the process. And yeah, I mean, this is how you would go about solving for accelerations of systems. Questions? Others? Yes? No one? Come on. So then what do you need to do to find the tension, Thomas? You use the systems approach to find the acceleration, then you free body diagram on either one, whatever you want. Free body diagram on, take one. M1. What are the forces on M1? Gravity and tension, right? Ft, Fg. And then we do what? Newton's second law. What does Newton's second law say here? My man! Oh, you rock. Explain exactly what was going through your brain. What did you just do? Thought about the coordinate system. In other words, what is this A telling us about down? Down is positive. Since down is positive, what happens to these two? You'd get Fg1 minus Ft equals M1A. So you always have to think about the coordinate system. It's totally crucial. All right. So with that, I want to talk a little bit about friction. This will be in the last 5 minutes. Tomorrow I want to give you guys a full time to actually do problems in class. I'm also going to be here after school to do problems. So, and you should have a lot of problems with the problems at this point in time. Yes. I think I moved it to Wednesday, just so next Wednesday. Yeah, so it's nice, and I would really try to do your best to just really have everything nailed down by then. Yes. I think, oh, the lab. All right, so let me talk to you guys about the lab. The lab, the data analysis is due on Thursday, but not the derivations. But you're still going to need to do the derivations to do the data analysis. So, and you'll understand what I mean. Do the derivations. Don't distinguish between inertial and gravitational mass. Just do it based on what we've done in class. Okay? Do that to solve, to actually fill in the data table. I want to look at your data table. So you don't need to hand in one each. You need to work with your group members to have your data set. That's the other thing. You need to work more together. If you don't have someone's number in this class, you better get it because you're going to need help. So I might even use these last couple minutes for you guys to exchange numbers or do whatever people do these days. I don't know how people communicate. If you saw my phone, have you ever seen my phone? Oh, this is great. There you go. I'm just kidding. Come on now, I'm a 20th century guy. I have my 20th century phone. So, all right. Yeah, your data analysis is due on Thursday. And I think the lab will be due probably Monday for you guys. Does that sound reasonable? All right. So that way I can address any questions you have. I want you guys to do well. And I think, we're actually at a pretty decent pace. So now the question I have for the group is this. Khalil specializes in exercises of futility, like teaching physics or moving boxes of not ordinary shapes. This is a flat, non-frictionless surface. In other words, this surface has friction. And I apply a force F onto A. And the question is, what can we say about the contact force on B? What can we say about the contact force? Well, we already know that net force is going to be proportional to the mass. That doesn't really help us in this case because there's friction acting on the system. And friction's external to these two boxes. How much time do we have? 12 seconds? Not bad. All right, let's leave it at that. And so the data analysis is due tomorrow. Just the data analysis. Okay? Not the analysis questions. So, this is the system that we're analyzing. Notice, is there friction? You bet there is. So this is an Atwood. This is a table Atwood, and there's friction. Is there a Boy Scout in the room? All right, Brendan, my man. You never knew that it'd be so useful. Yeah, unfortunately, I think the structure of the organization kind of gives the Girl Scouts a short shrift. Is that the right term? So there you go. Notice, if I put this on there, what do you have? Static friction. If I go and, let's say, remove that, and, all right, so now let's take a look at this a little bit closer. Okay. I'll add another 20. I'll add another 20. I'll add another 20. I'll add another 20. And there you go. What does that represent? What does that represent? Be careful. What? Guys, you know by now that physics doesn't work. All right, so, well, why? Why me? All right, so yeah, so. You get where I'm trying to get at, right? What am I trying to get at? The peak static friction is the second case. So if you take a look, I think this is roughly the peak static friction point. Or if I remove one, you can see that. If I remove one, physics all of a sudden works. So here's your three cases. So we go and we do a free body diagram. And what do we do a free body diagram on? Everything. Okay? And call this M1. Call this M2. So, free body diagram on M1, what do we have? Tension going up and gravity going down, Fg1. Notice I signify all of my forces of gravity. I make it specific to the mass. In other words, that's mass 1, so it has Fg1. Don't be lazy. M2. What's on M2? Tension. Which direction? Ft to the right. Actually, let me separate out my FTs. Ft1, Ft2. What else? Spit them out. Gravity, normal force, right? Gravity. Normal force. And friction. Notice I'm not specifying which friction. Why? Yes? That's right. You have your three scenarios. So we write down Newton's well, what coordinate system do you want? Down's positive, to the right's positive. Boom, positive, positive. So then what does that tell us about A1 and A2? They're both equal and positive. So A1 equals A2. So then I write Newton's second law. What does Newton's second law say for each body? Says net force on body 1 is equal to M1 times A1, right? So what are the forces on body 1? Just tell me. That's Fg1 minus Ft. And little heads up, what can we say about Ft1 and Ft2? They're equal. Why? Why are they equal? What is this? What is this? Strings massless and pulleys massless. So, Fg1 minus Ft equals M1A1. And then what do we have for M2? We have two sets of Newton's laws, one for the y direction, one for the x direction. In the y direction, what do we have? What do we have in the y direction? So net force on body 2 in the y direction is going to be Fg2 minus Fn, and that's equal to m2a2y. What is a2y equal to? 0. So this gives us something pretty obvious, that what? Normal force is the weight of body 2. And what's the weight of body 2 equal to? m2g. Since we have Fn, I might as well then go and calculate the two forms of friction that we can calculate with it. What two forms can we calculate with it? Which static? Max static. So we can find FFS. We can express FFS max. What is that equal to? Mu S Fn, which is mu S m2g. And, yes, same difference, yeah. Peak, max. It's like the top of a mountain is its peak, and it's also the maximum height which you can ascend. So, the kinetic friction is the other thing we can calculate, or we now know. That's equal to mu k Fn, which is mu k m2g. And we just keep those in our back pocket when we get there. Now we write Newton's second law in the horizontal direction for the table, mass, or for M2. And what do we have? Net force on 2 in the x direction, but let's not really distinguish it. It's M2A2, but that's equal to M2A1, correct? In other words, what did I just sub in? A1 equals A2. So what are the forces on this body? Wait, what are the forces on this body in the x direction? It's Ft minus Ff. All right, so here you have your two equations. Yes? Wait, we're not dealing with the case. We'll just leave it general for right now. Okay? So we just want to leave it general. So what do we have? We have the following two equations. We have this, which I'm going to lasso, copy, paste. Where that paste? Undo. Okay? Maybe I'll even move it here. So here's our two equations. Guess what I'm going to do with them? What am I trying to eliminate? What do I not know anything about? Tension. So let's eliminate that first. How do I eliminate that? By add them. You can solve by substitution if you like inefficient methods. So what do you get here? Fg1 minus Ff is equal to? And now you're starting to get suspicious. Or at least if you haven't, you should start getting suspicious. Anybody want to know why you should start getting suspicious? Yes? No, that's true, but that's not why you should start getting suspicious. Because anybody start seeing a pattern with these systems? About like what you end up with and what you start with? Yeah. Yeah, there's something that has to do with those two bodies. And then if you look at the right side, it's the total mass And you'll see this is actually alluding to what's called the systems approach, which you're not allowed to use for the lab, and generally speaking, you should use with great care. But I'll get to that a little bit later in this lesson. So here you have it. So now let's actually analyze the three scenarios. The first two scenarios are very straightforward. So the first scenario is you're not at the maximum static friction, but it's static friction. So let's actually look at this. So what you have is, so scenario 1, FFS. So what do we have? We have M1G minus FFS is equal to M1 plus M2 times A1. But what is A1 equal to? 0. And so what do we end up with? That M1G is equal to FFS, which just exactly makes sense. What is that saying? That's saying that the force of static friction is precisely equal to what? The weight of the hanging mass. Does that make sense? Right? Because it can't be greater. If it was greater, what would you observe? What would you observe if this was greater? The force of static friction exceeded that. You would exceed that, move that way. All right. You don't want to see that. All right. So now the second case is FFS max. So for FFS max, what can we do? We can replace FFS with FFS max. We get M1G minus FFS max equals M1 plus M2 times A1. But what's A1? It's 0 yet again. So yet again we have FFS max equals M1G. But we have an expression for FFS max. 1 second. What is FFS max equal to? Go back in your notes. It's mu s Fn, which was mu s times M2G. So what does this give us? This gives us a means of doing what? Measuring the coefficient of static friction. This is now a new means of measuring the coefficient of static friction. Notice it's equal to M1G over M2G, which is M1 over M2. So, now you say, Mr. Khalil, show me the money. All right, so here we go. How am I going to do this? Well, here's your scale. Okay? So first things first. I'm going to do something very simple. I'm going to take all these. I'm going to have you tell me what this value is. Thank you. Thank you very much, sir. Thank you. It was very kind of you. Very kind of you. Calculate that value. What do you got? Yeah, you have time. Don't feel like you're being pressed. 780. All right. All right, 780. Write that down. Now let me throw this on the scale. What? All right, that scale is balanced. It's not 300 grams. It's over 200. And this is 2. This right here is 241, guys. Got that? Wait, no, it's 240. 240. So 240 plus 780 is how much? 240 plus 780 is what? So it's 1.02 kg, right? And then, what do we have here? Count that. Ooh, that was nasty. My God. What is this? Yeah, but so? $230. So you have 230. M1 is 230, right? M1 is the hanging mass. So we have point M1 is 230. M2 is 1.02, right? And this was roughly. So what do you get from mu? I can't hear you. What do you get from mu? Let's just verify that this is roughly what it takes to move this mass. So, do you have those other two? Can I have those other two? Thank you, sir. So what do you got? You got 0.23. So in other words, mu s equals 0.23, right? So now what do I do? Guys, tell me, what do I do? What do I do? How do I tell if this is right? What do I need to do? I go and I start collecting data. Because remember, we have another means of doing this, right? How much mass is on here? 1.02 kilograms, right? So therefore, the normal force is what? What's that normal force? Like, come on, get out your hamburger helpers. Start plugging it into that calculator. Got to use it for something in this class. It's 1.02 times 9.8. What do you get here? So it's 10. So now, let's actually go. I need someone to hit play. Good. No. Sorry, that's fine. What's this? What value is that? This value is 3.67. Let's try this again. Because it looks like physics doesn't work. So, what do we got here? Ah! Click play. All right. Now, it looks like this didn't work either, but it looks like it's about the same, about 3.2, 3.3. And so what is the conclusion? Physics doesn't work is the correct conclusion. Nice job. All right, I need to step away. 1 second. One day I will kick this cold. So physics doesn't work. But the general idea is this. If I have some type of independent means of measuring mu(s). And, it's kind of questionable which one is actually more accurate. Which one do you think would be more accurate of the two? Yes. I would argue that using the outward would be the more accurate one. Why? Because I can modulate the amount of mass that I add on to the hanger in a much more controlled way than I can modulate the force with which I pull. Do you understand what I mean? In other words, how much can I modulate the mass I add on to the hanger? I can increment it by how much? No, I can do less than 20 grams. I could do it by 5 grams, 5-gram increments. So what does 5-gram increments translate into in terms of newtons? How many newtons? 5-gram increments would be what, 1/20th of a newton? Which is how many pounds, like roughly how many pounds is that? How much? 1/10 of a pound, right? So now 1/10 of a pound, do you think you can actually adjust your force by 1/10 of a pound that you're pulling? No. So I would argue that this is giving me a much better measure of the coefficient than this is. So going back, now that, another demonstration failed, and you guys completely trust science. Yes? I would argue that the major reason was the inability to modulate my force with so little mass on the table. So if you look at it, that was the first source of error that I gave you guys in my write-up. So, and I could go in and test it and redo it, but I don't want to waste your time. You guys have a lot to do between now and next Wednesday. So we now have another means of measuring mu. So now we go to the third case. And what's the third case? There's kinetic friction. So in the third case, we have the following. We have that Fg1 minus FFK is equal to M1 plus M2A. Right? Solve for A1. What do we get? We have M1G minus mu K M2G equals M1 plus M2 times A1, which means we can solve for A1 very handily. A1 is equal to M1G minus mu K M2G over M1 plus M2. Now, this does tell you a little something. What's the maximum value that mu K can have? It's not obvious. What's the maximum value that mu K can have? Well, assume that M1 equals M2. If M1 equaled M2, what's the maximum value mu could have? 1. Why? That's right. In other words, that acceleration cannot be negative. So, in other words, this has to be a positive number. Otherwise, you would observe the system accelerate in the opposite direction. Not going to happen. So, Now let's solve for the tension. So to solve for the tension, what do I need to do? I need to go back to the original equations that I used. So probably the easiest one would be to deal with M1. For M1, what did we have? We had FG1 minus FT equals M1A1. Is that correct? Solve for FT. What do you do to solve for FT? Rearrange this. You get FT equals M1A1, M1G minus M1A1. What did I do? Added FT to both sides, subtracted M1A1 from both sides. Or another way to do it is to say, I'll flip those. I'll just rearrange them. So, start plugging in. What do you get? You get M1G minus M1. What's A1? It's that monstrosity up there. It's M1G minus mu K M2G, all divided by M1 plus M2. Now what? Yes? You could. Now what? We need a? That's right. Say it like you mean it, Emma. That's right. What's our common denominator? M1 plus M2. And so she didn't want to say it because she'd be like, oh, that's going to be nasty. But whatever. The way you do it is you multiply M1G by 1. And the one you choose is the strategic one. Notice, what did I multiply M1G by? Ooh, I multiplied it by a number. 1. How did I make my 1? I made it by taking the denominator and dividing it by itself. So now I multiply everything out. What do I get? Spit it out. I want to hear you guys. Distribute that M1G. What do you get? M1 squared G plus G minus M1 squared G plus mu K M1 M2 G. And all of this is over nice. So, what does this mean? This means we have some cancellation. What's our cancellation? M1 squareds. And what are we left with? Notice, what do these two share? M1, M2G. So you factor that out. What are you left with from this term? What are you left with on that term? There you go. So now let's analyze this. What happens if mu is 0? In other words, mu equals 0 means this is, what is it? Mu equals 0 means no friction, frictionless surface. If mu equals 0, then what does this reduce to? I can't hear you. Right? What should this correspond to? Anyone? That should correspond to the force of tension you're supposed to derive in your lab tomorrow. Right? So now, notice. Anybody notice something? Take a look at the hanging outward derivation. Remember the hanging outwood? Where you had the elevator, that thing? Go look at the tension in the hanging outwood. What do you notice? It's twice that. Anybody want to come up with a physical explanation for why the tension in the hanging outwood is double the tension in a frictionless table outwood? Yes.
Because the string is experiencing 2 times the force of gravity.
Correct. In other words, the string is supporting the acceleration of 2 bodies against the force of gravity. Whereas in the case of the table outwood, it would only be, or half of the mass of the system is supported by the table. Yes? Yes. Yes, same concepts. Which one are you referring to?
The one where you have like the 2 masses, the one trigger mass coming down either side, pulling the...
Slightly different. It's a slightly different concept. You're talking about one being held by 1 rope versus 2 ropes?
No, it's the one that you have, you have one thing that's connected to 2 ropes and they're going down masses, and 9.8 is what it's reading.
Okay.
And the other one only has 1 mass connected.
Yes.
Both the same.
They're both the same. No, it's slightly different. That's slightly different. So, but anyhow, it's a good mnemonic to actually kind of keep the 2 in mind. The hanging outwood versus the table outwood. That the tension, the hanging outwood is double the table outwood. So now let me try a different problem. And this problem is actually quite interesting. This is the one that you guys probably have the most experience with. Anybody recognize what this is? This was a chain that was from, I don't know, what is it? The stage chain? People who do drama or something? So I'm sure you guys have all seen this, right? You have all seen this phenomenon. And you know what phenomenon I'm talking about, right? What? First, is this a massless chain? No, it's not. All right, this chain has mass, so what's going to vary along this entire chain? Well, the first question I have is, what am I going to do with it? What do you think I'm going to do with it? Ready? What am I trying to overcome here? That's right. Come on. Tape out of here. What do you expect to happen? Mr. Quinn, you're about to see it. Ready? Come on. All right.
See what you need? You need a floor that's longer than the length of chain.
Yes, you do. That's what you really.
Really be seeing some real non-uniform accelerated motion.
That's right. And in fact, that's the problem that we're going to do. The problem that we're going to do is that, but with a floor like we're dropping it off the building. So, let's do it. All right. So first, is the acceleration uniform? Is the tension uniform? Is the tension going to be uniform? No. No. All right, so now we need to set this thing up. So we're not in Kansas anymore. Just a little heads up. Oh, God. Anywhere but Texas. So here is your table. And the question is, you know the question, easy or hard? Oh, come on, are you crazy? Come on, let's do the easy one first. Okay, easy one. And what do I mean by that? Do I include friction or not? Yes or no? All right, let's hold up. It's not that hard to include after the fact, but I think it's a bit of overkill. So let's not include friction initially. So here's your table, and here's your chain. Okay. So now, I need to give you some parameters. Mass of the chain is m. Length of the chain is L. That's right. Oh, you guys are pros already. So we know the mass, we know the length, right? So naturally, if there's nothing hanging over, what's going to happen? Nothing, all right? We know nothing's going to happen if nothing's hanging over. So we hang over a little bit. What's that little bit that we hang over? What is it? How about X? Or maybe, you know what, since it's in the vertical direction, let's call it Y. So that means how much is on the table? So that's L minus Y. And so now, guess what I'm going to do? Well, first I need a coordinate system. So what coordinate system works? Positive, positive. That's right. So in other words, this coordinate system. You never thought you would be rearranging your coordinate system this much. But you'll see, you guys are actually much better than my class last year. You're much better off. So, I was a little bit more rigid about coordinate systems last year. This year, I'm actually glad that I'm not so rigid. So now I'm going to do something very strategic. I'm going to look at a single point. And take a guess which point I'm going to look at. Oh, it's pretty obvious, right? I'm going to look at this point right here. And why do I want to look at a point? Because what can I say about the force of tension at a point? If I took two different points, can I say the force of tensions are equal? No, but if I took a single point, what can I say about the tensions? It's equal. So let's actually go through this. So, and now I'm going to look at my two segments. Here's my two segments. Free body diagram. So what's the force? So I should probably call one M1 and one M2, right? Maybe I'll call this one M1 and call this one M2. So what are the forces acting on M1? Gravity and tension. And where is this acting? It's acting at the top. So do I need to? I did it at a point. What about here? What are the forces acting on the second body? Gravity, normal, tension. Is that it? Oh, is there friction acting? No. Why? Because we're not sadists. We are not sadists yet. We'll leave that for the second half of this period. So, so here's Ft, and then there's, of course, Fn and Fg2. And notice, what can we say about the vertical forces? Do the vertical forces matter? Why? No, no, no. I can't stress this enough. The vertical forces don't matter on the block on the table because there's no friction. In other words, you always have, if there's friction present, you have to consider it. Why? Because you need what quantity? The normal force. Just a little heads up. It will save you time when you're solving problems on the exam. So we'll just look at each of these. So now net force equals mass times acceleration. Let's do it for M1. So what are the forces on M1? Spit it out. Very good. Fg1 minus Ft equals M1 A1. What about the forces acting on M2? Ft equals M2 A2. What can you say about the A's? Why? Because it's at a point. That's right. So the A's are equal because we're analyzing this at a point. So here are our two equations. And so I might even replace this. I might even say, you know what? This is Fg1 minus Ft equals M1A. And this one is Ft equals M2A. Anyone who did the derivation should recognize this. What does this look like? It looks just like the table outwould without friction, right? This is it. So what do? Add them. What do you get? And so what do you get? You get A is equal to? What's Fg1? M1G over. Does that surprise you? No. But let me ask you a question. Are we done? For the acceleration. Why? It's not constant. Aha! But wait a second here. What can you say about that chain? Come on now. What can you say about that chain? The chain is made of the same material. Each link is the same. So therefore, it's called uniform. It's uniform material. What does that mean? Same density. What does that mean? It means if you take any piece of length, right, it'll have the same mass per unit length. Correct? Let's use that. So what does that mean? That means we set a proportion. That means that M1 divided by the length, which is, what's the length of M1? Y is equal to the total mass, which is M over L. And what do we get? M1 equals? And what does M2 equal to? Let's see if you guys can just jump straight ahead. What is M2? Come on now. Come on now, do the same thing. M2 over M2 over L minus Y equals M over L. So therefore M2 is and so then what do we get here for the acceleration? Times G over m1 plus m2. But what's m1 plus m2? And don't you dare plug that into that equation. Like, don't go and say it's y over L plus times m plus, it's just m. That's right. How is it just m? Because m1 plus m2 is the entire chain. That's right, it's the entire chain. And so what do you end up with? Is that uniform? No, it's not. Notice the acceleration is a function of the length of the chain that's hanging over. Sweet. So now I'm going to ask you a question. Tell me, what does this graph look like? A versus Y. It's linear? What is it? Whoa, be careful. The table, the setup was that the table was much higher off the ground than the chain. So in other words, we're dropping out of the window. So what's going to happen in this case? But you're right. It's going to be linear. Until, and what is that constant value going to equal? That's right. Notice when y equals L, what is A equal to? G. So this looks like this. But notice that's A versus Y. We haven't dealt with that graph yet, right? What do we generally deal with? A versus T. And V versus T. So what do you think A versus T looks like? Well, I'm going to tell you something. You're not going to know it. You're not going to know it based on this. But one thing you might be able to figure out is what V versus T looks like. What V versus T looks like, you might be able to figure out. So what do you think V versus T looks like? So it's going to be, we know it's going to be increasing, right? Think it'll be slow or fast? What do you think, Brendan? It's an exponential graph, but what happens? It's an exponential graph that becomes linear, right? So wait. Damn it. Is that linear? Does that look linear afterwards? In other words, it's exponential up to what point? When when y equals L. It's exponential. And then once y is greater than L, it is linear. And what's the value of the slope? Here? What's the slope here for the linear portion? That's right, slope equals G for this portion. So now A versus T is a little bit harder, and you're not going to be able to infer A versus T without calculus. You need calculus to find A versus T. And actually, A versus T looks like this. It's actually exponential and then flat lines. Interestingly enough, this is called a hyperbolic cosine function. Yeah, it's a combination of exponential. It's an exponential growth function, but it has very special characteristics. So, and this you can't really infer from here. You need the mechanisms of calc for it. But notice how far we were able to get without it. It's incredible. But what haven't we solved for yet? Maria, what have we not solved for? We solved for the acceleration. What did we not solve for? Tension. That's right. So we go and we solve for the tension. And you're like, Khalil, this has got to end. The madness must end. But it gets better. It just keeps getting better. It's just like, so we have, which equation do you think you're going to use to solve for the tension? That's right, Ft equals m2a. And what's m2? So it's m times L minus y over L. And what's A? Y over L times G. And so there you go. There's your force of tension. So can I take this and move this somewhere? Maybe I'll move this guy. Oh, that was interesting. Oh, that's fascinating. Look at that. All right. You guys aren't as excited as I am about these things. You just haven't spent enough time. All right, so here's your expression. So let's clean this up a little bit. We get Ft is equal to m over L squared times Ly, well, there's a G here, minus y squared. Naturally, I'm going to ask you what? Those you were in pre-calc that had an exam yesterday. You know who you are. Where's the maximum tension? Maximize the tension, guys. In other words, at what value of y is tension maximized? And don't blow it off, because guess what you're going to have to do? You're going to have to do this on the next lab. So just in case you thought mathematics was something that you cram the night before the exam, and then dump the day afterwards, realize that everything that you use and commit it to memory, we're going to be using 10 times over. How many people cram and then dump? All right, we got some honest people in here. That is the lowest, it's the lowest form of learning. I remember doing it all the time. It was terrible. So here you go. I want you guys to spend 5 minutes trying to figure out how to maximize it. In other words, find the value of y that maximizes it.
Just explain how you first went to deriving these.
Density is uniform.
Density uniform. Did you substitute it for two guys?
So the density is uniform. So m, this piece, has mass m1
Yeah.
and has length y.
Yeah.
That's going to be equal to the entire mass of the chain divided by the length of the chain.
Okay, that makes sense.
All right. You're not going to solve problems with your hand on your head. Come on now. What do you have to do? Oh, my God. He's hamburger helping it. That's so bad. Come on, grab that thing. Graph it. What do you mean, how do you graph it? What's your parameter? Oh, the hamburger helpers. It's great. Come on, look at that. What do you see here? I see a quadratic. Right? So, graph that. What is that going to look like? Ft versus y. At y equals 0, what is that going to be? 0, right? At y equals L, what is that going to be? 0, right? What can you tell about, is it concave up or concave down? Down. How do you know this? Because the coefficient in front of the squared term is negative. So it's 0 here, and it's 0 at L. So therefore, what's that going to look like? Right? Guess what you have to do now? You have to find the... Yeah, what is that called on a parabola? The vertex. Who had an exam on this? Oh, yes. Oh, man, that's good stuff. Find that vertex. Very nice, Noah. The vertex is at 1/2 L. Does that make sense? In other words, at Y, you could have also done this by symmetry. Why? Because we know that this is symmetric between 0 and L, so at L over 2, that's where the vertex will be. Now the question is, does this make sense that the tension would be maximized when half of it is hanging over? Yes or no? Yes. It makes a lot of sense. I would like to point out something as well. What's the tension in the chain when it's falling? When all of it's falling? 0 is correct. It's in free fall. Pretty awesome problem. Yes? This is a great question, Mika. Oh my God. I want you guys to think about that. He said, will it fall like this or will it rotate? And the answer is it has to fall straight up unless there's external forces present. Why? Because what would be required to make it do this? It would require a force. Although I don't know. You know what, Mika? I don't really know the answer to this question. I think I may be able to answer it in a few units. But I'm pretty sure it will fall like this. No, there's external forces present. So, with that, I guess, any questions on the homework? This would be a good time.
Yeah.
Yes.
FRQ number 10.
FRQ number 10 can wait.
Why?
Because this is like I am ready for hell problem, right? You know, when you're going to battle Satan, this is the problem that you do right beforehand. All right? Well, I mean, the reason I'm holding that off is that is the problem that you'll know you're prepared for the exam for. And I am not going to spoil it for people. Huh? Well, for that problem, no, because that problem is like, that is a problem that you'll know. If you can blow through that problem in 15 minutes, you'll know you're ready for the exam. Yes?
I just did the free body diagrams for
Number
number 2.
2?
I just don't know if I'm right.
All right, so let me that is a straightforward problem. This is the one on the elevator, right?
Yeah.
If you're in the elevator, what do you feel?
I feel a force when it's going up.
So in other words, what forces do you feel, period? And normal force. You feel anything else? No, that's all you feel. Those are the forces you feel.
No, like applying force, but
Is there anything applying force to you? Remember, physics is about forces. Forces is about feelings. Physics is about feelings. Yes.
Number 17.
17. Read it.
Two boxes of masses M and 3M on stacks.
M and 3M. So M is on top of 3M.
Yeah. The surface between the more massive box and the horizontal surface is smooth. And the surface between both boxes is rough.
Mm-hmm.
The less massive box does not slide on the more massive box. What is the coefficient of static friction between the boxes?
So wait, is a force pulling on this?
Yeah, doing that.
Which one?
3M.
All right, so you have an F going on 3M. So what am I going to do? I'm going to create a system. And guess what that system's going to comprise of? The whole thing. Here's the blob, 4M. What's the external force on this system? F. Where's it directed? To the right. Net F equals MA. Right? What's the net F? What's M? 4M. Solve for A. A equals F over 4M. Right? Free body diagram on this box. What are the forces on this box? Normal force going up. Gravity going down. And friction going to the right. Right? What are we solving for? All right, nice. So, what do you have here? You have FF equals mu Fn equals mu mg. Correct? So now, what's the net force acting on this thing? Net force is equal to the mass times the acceleration. The net force is FF. And that's equal to the mass, which is m, times the acceleration. But what's the acceleration of this body? F divided by 4m. Why? Because what does it not do? It doesn't slip. That's right. So this is F over 4m. But what's FF equal to? Mu mg. So what do you end up with? M's cancel. You have mu mg equals F over 4, which means that mu is equal to F over 4 mg. Oh, everyone hand in FRQ number 1. Or even better, take a picture of it. Send it to me. The first free response question. I need to keep you guys honest, or semi-honest at least. Take a snapshot, email it to me. I don't want to steal away your free response questions. Thank you. Huh? No, just send me the picture. The reason why is actually I found it was somewhat useful. Because what I'll do is I'll go and click through each one. And then if you make a mistake, I'll actually type back to you and tell you what your mistake is. Because I think several people made critical mistakes on this. And it's an easy problem, so I can actually just spot it. And then I guess I could walk through the halls and do the same thing, but at the same time it takes up class time. So, other questions? Anyone? Yes. Number 20. Number 20? Yeah, number 20. Number 20, indeed. Which one is this? Is this with friction? All right. Hold off on this question because I need to do that derivation. I need to actually show you stuff with that question. Number 18. Which one's that?
It's 4 kilograms block moving between.
Let's hold off on that. We still got another day for that. Yeah, it's a tough problem. 18, 20 I need to do the derivation for. I think that's one of the last pieces of the last lessons. What I'm going to do right now, I want to show you guys the systems approach to solving Atwoods and stuff. That's fine, because that will show you the power. So, There it is. That's what a joke. What? That's not coming up, Mr. Khalil. It's Z Khalil at West Morris Regional High School District.org. All right, so take this, M1, M2. Which one's greater, mass? Tell me. Say M2 is greater. So now I have a question. When you look at this as a system, what do you see? What do you really see? You see the force of gravity on M2 driving the system, right? And you see the force of gravity on M1 doing what to the system? Retarding it. That's right. That's right. So it's like drawing it along a single line. So in other words, you can actually have this system called MS. And what's MS equal to? That's right. M1 plus M2. And what's drawing it down? Which one? FG2. And what's retarding it? FG1. And then we write Newton's second law for this system. What's Newton's second law for this system? Net force is equal to MS times A. This is in general. This is an Atwood. This is not a problem. I'm showing you guys how you're going to actually solve systems on the multiple choice part of the exam. Because what's the net force here equal to? Well, what do you want to call positive? Let's call down positive. So what do you have? You have FG2 minus FG1 equals, what's the mass of the system? M1 plus M2. Right? Times A. What does this equal? M2G minus M1G equals M1 plus M2 times A. So what is A equal to? Notice how quickly we got that. How quickly did I just solve for the acceleration of that system? Very. It literally took seconds. It gets better. Let's look at the table, Atwood. It's called the systems approach. Notice, what can I not solve for? Why? But why? Why is tension? Why can't I solve for tension? No. Tension is an internal force to the system. It's internal to the system. What is the sum of all internal forces to a system? Zero. What is that called? Newton's third law. What does Newton's third law say? F of 1 on 2 equals negative F of 2 on 1. Right? Here's your two bodies. So F of 1 on 2 plus F of 2 on 1 equals 0. What does this mean? This means if you actually take a system of two bodies and you were to encapsulate that and look at that system and ask yourself, what is the sum of the internal forces, you would get 0. And what that really means is that when you're looking at, let's say, an Atwood, and you do the systems approach, you can't solve for the force of tension because it's internal to it. It does not contribute to the overall system. So what contributes to the overall system? The external forces acting on the system. So let's actually take this approach. And I'll ask you, find the acceleration of the table Atwood with friction. with friction. Tell me. M1. M2. Goodbye. Tomorrow, hopefully we'll have time to go over the Unit 1 exam.